Today on How It's Made. Gummies, aluminum cans, fish farming, and bronze sculptures. There's nothing kids love more than candies they can pull and stretch, which probably explains why gummy candies and licorice have always been stick-to-your-teeth favorites, except with parents who don't have a family dental plan. Everyone calls this red licorice, but there's actually no licorice root in it. The ingredients are wheat, sugar, and corn syrup with red food dye and both artificial and natural strawberry flavoring. They cook the mixture for 2 hours at 102 degrees Celsius. This slowly forms a thick paste. They cool it down, then put it through extruders. The extruders work like icing nozzles, shaping the paste into a design such as the twirls we see here. A water-lubricated knife slices the continuous strips into 18 and 21 centimeter lengths. The water also rinses off any licorice buildup on the blade. The cut licorice goes on aluminum trays. The stacks of trays then go into an oven to dry for 8 hours at 60 degrees Celsius. As the excess moisture evaporates, the licorice shrivels. Workers weigh the correct amount of licorice for each package. To make gummy candies, they use what are called printing boards, large sheets with raised shapes. To make gummy worms, for example, they mount the gummy worm board on a stamping machine. The machine then stamps the worm shapes onto trays of cornstarch. This creates a series of cornstarch molds for the gummy worms. While that's going on, another machine mixes gelatin, sugar, corn syrup, color, and flavoring and cooks the mixture at 115 degrees Celsius. A machine called the depositor pours the mixture into the cornstarch worm molds. The molds then go into a refrigerated room. In 12 to 15 hours, the candies cool and solidify. A machine then flips the candies out of the trays. The cornstarch molds disintegrate. As they fall downward, the machine sifts out the lumps, then recycles the used cornstarch into new cornstarch trays for the next batch. The candies go through a cleaner. As they spin, air nozzles blast off the cornstarch. The next drum coats the candies with mineral oil to make them shiny. Children love gummy worms because they're gooey and slippery and wiggly. But it's not just kids who are hooked on them. Many fishermen actually use them for bait. Before packaging the candies, the workers weed out any that are stretched out or stuck together. Wonder if they get to eat the rejects. prion is what causes killer neurological diseases such as mad cow in animals and Creutzfeldt-Jakob in humans. It's a protein normally found in the membranes of cells. Scientists are trying to determine what changes that protein to an abnormal form to cause these fatal brain diseases. The next time you buy a canned soft drink, consider this. That aluminum can will always be recyclable. Unlike plastic, aluminum never deteriorates, no matter how often it's melted down and used again. Aluminum cans are so lightweight that it's hard to believe they're made from a huge roll of aluminum sheeting that weighs 9 metric tons. The sheet is about 1.5 meters wide and as thin as construction paper. A roll like this is long enough to make 750,000 drink cans. The sheet feeds into a press that punches out round pieces that'll be formed into cans. The punch press actually performs 2 operations. It punches out a disc 14 centimeters in diameter, then bends it into a cup. What's left of the sheet gets compacted and sent back to the aluminum factory where it's recycled into new rolls. The cup goes into a machine called the draw and iron body maker. A tool draws out the aluminum, forming the body of the can. The tool is lubricated so it won't tear the aluminum while stretching it. The lubricant also acts as a coolant because the aluminum heats up as it's being worked. Once the body is formed, a trimmer cleans and straightens the edge. Now the cans move along upside down on the conveyor belt over to the washer. The washer performs a 6-stage cleaning. The first 2 washes are in hydrofluoric acid at 60 degrees Celsius. The last 4 washes are in deionized water, neutral water with no pH, also at 60 degrees. The cans come out of the washer and go under a hot air dryer. They're now shiny because the hydrofluoric acid wash removed a thin surface layer of aluminum. Next, a roller passes over the cans, coating the bottom rims with varnish. This varnish coating allows the cans to slide easily on conveyor belts and in vending machines. It shows up as a blue ring under ultraviolet light. The cans are now ready to be printed. This rotation printing system can apply up to 5 colors, one at a time. The machine then applies a layer of varnish to protect the ink. This is what the print and varnish process looks like in slow motion. And here's the actual speed, 1,800 cans per minute. Next, the cans fly through an oven that instantly hardens the ink and dries the protective varnish. The next machine sprays a water-based varnish on the inside of the cans. This creates a barrier between the drink and the aluminum, so the drink won't end up tasting like metal. It also prevents the aluminum from being eaten away from the inside by the acid in carbonated drinks. Next, the cans go through a machine called the necker, which forms a 5-centimeter neck on the can. This is done gradually in 11 steps so as not to puncture the paper-thin aluminum. The next machine, called the flanger, forms a curved-over edge at the top of the can, which will later attach to the pull-tab cover. The cans pass through a sophisticated vision system that photographs the inside of each can. Any can that doesn't meet standards, that has a bump or ink inside, for example, is automatically canned from the production line. They strap the finished cans onto a pallet. From here, they're shipped to the drink company, which fills them, then attaches the pull tab cover. Fish farming generates about 20% of the world's fish production. Some fish farms are very high-tech, while others use more traditional methods. Fish farming began in 2000 BC. If these rainbow trout are going to have the energy to make baby trout, they'll have to be well fed. On today's menu, ground shrimp. The fish farmer gives the mating process a hand. He takes the female fish and presses on her belly to squeeze out her eggs. A 1-pound fish has about 1,000 eggs. It takes about a minute to get them out. Next, he takes the male fish and squeezes out his sperm. This also takes about a minute. The fertilization process is pretty low-tech. No microscopes, no test tubes. The farmer mixes the eggs and sperm by hand. He then rinses the eggs with clean water. He repeats this step 7 or 8 times until the water runs clear. The eggs that stay at the surface are duds, so they are discarded. The farmer transfers the good eggs to bottles, then fills the bottles to the top with water. The eggs incubate for about a month. By the 25-day mark, if an egg is alive, 2 little black dots appear. Fish eyes. After the incubation period, the farmer empties the bottles and spreads the eggs on a surface with slats. The eggs lie here underwater until they hatch 10 to 15 days later. The newly hatched trout swim down through the slats into the basin below. The baby trout feed off their placenta for the first 18 days. After that, they eat special trout food made of fish meal. The trout grow to about 8 inches long by the age of 8 months. At that point, the smaller trout swimming around them start looking pretty appetizing. So the farmer has to classify the fish by size and move them into separate basins. Trout reach adulthood at the age of 1.5 years. Now the farmer transfers them into his man-made lake. From here, the fish will go to market. But before they leave, the farmer mates them, starting the cycle all over again. Bronze is the oldest metal alloy known to man, and it's ideal for casting works of art because when molten, it flows into even the tiniest crevices of a mold. This allows sculptors to achieve incredible detail in their work. Man first discovered how to cast metal around 3500 BC, during the period known as the Bronze Age. Many civilizations honored their royalty and gods with bronze statues. When it comes to art, the late 19th century French sculptor Auguste Rodin was the master. They say his bronzes were more lifelike than the subjects themselves. Bronze is also a popular medium for modern art. Sculptors first carve a replica of their sculpture from wood, or shape it out of plaster or clay. They coat it with a lubricant, then with silicone rubber. When the rubber hardens about 6 hours later, the lubricated replica slips out easily, leaving a detailed rubber mold. Next, they pour hot wax into the mold. The wax cools in about 15 minutes, leaving an exact wax replica of the sculpture. Next, they attach what's called a sprue, a wax channel that will funnel the molten bronze into the mold. They dip the wax replica into a ceramic material. Then coat it with powdered silica, a common mineral, to strengthen the ceramic. Next stop, an autoclave. In about 10 minutes under the machine's hot steam pressure, the wax inside the ceramic shell melts away, leaving a hardened and hollow ceramic mold. That mold goes into a kiln at 850 degrees Celsius. After 2 hours, it's fired. This is the finished mold into which the bronze will be cast. At the foundry, they heat the bronze to 1,140 degrees Celsius. Then carefully pour it into the mold. The molten metal takes just a few minutes to solidify. Then they chisel off the ceramic casing to reveal the bronze statue inside. They sandblast the statue to remove the ceramic residue. Then they saw off the sprue. They weld shut any holes or other imperfections. Then polish the statue using various abrasive heads. They heat the statue, then spray on an acid coating. This coating, called patina, gives the bronze its shimmer and richness of color. finally, a coat of wax makes the statue shine. If you have any comments about the show, or if you'd like to suggest topics.
Hello everybody, I'm Mark Tewksbury, your host for this program. Our goal is to reveal the methods and materials that turn out the products we see every day around us. There's a whole new world of things waiting for us to discover here on How It's Made. Casein and whey are milk proteins. Researchers are using them to make packaging to seal prepared foods like pizza. The product is a protective film that conserves food longer, in fact up to 10 days longer, without changing the food's flavor whatsoever. How convenient. On today's show, bicycle helmets, aluminum, new technology brakes, lithium battery cells. I like riding a bike, and I also value my life, which is why this solid safety helmet is a must. Not bad looking either. A bicycle helmet is constructed of an exterior shell and an interior one of polystyrene foam designed to absorb shocks. Some designs for bicycle helmets are drawn by hand and with computer-aided graphics. The design has to take into account that it is not on a flat surface but on a rounded one. This creates optical deformities that have to be corrected. Fabrication begins with the exterior shell. This polymer sheet is heated in a heat former at a temperature of 65 degrees centigrade. The mold lifts the sheet and suctions it to fill all the cavities of the mold. This operation lasts about 1 minute and produces 4 shells. Then, when cooled down and hardened, the 4 shells are cut by hand. Ventilation openings are cut with a heated wire apparatus. These openings have been preformed during molding of the shell. The heated wire easily and neatly cuts the polymer. Next step, trimming the helmet to eliminate excess polymer. The circumference is manually cut using a router. The edges are then sanded to even them. It is also possible to cut the circumference of the shell with a heated wire. This operation takes more time but is more precise because of the resulting cleaner cut. Now they're going to fabricate the foam interior that will be placed inside the shell. It's made of polystyrene beads that will expand and bond together. This expander increases the volume of the granules that fall into it. Steam and an agitator let the polystyrene beads expand uniformly. The granules are now ready. The contents of this bin will be able to produce about 20 foam pieces, which will take shape on these molds. The press closes up for the 6 minutes that it takes to mold 4 foam pieces. The particles fuse with steam before being cooled with water. The foam is removed from the mold. Forms are produced for different helmets. Fusing of the particles has welded the granules to one another. Depending on the helmet model, openings have to be made with this heat iron to allow for installation of an air vent accessory. All that remains is to make the adjustment pads, cut with this press-powered stamper. The adjustment pads are held in with Velcro to allow easy adjustment of the helmet. This allows the cyclist to change the foam pads for greater comfort. Inserting the straps calls for good manual dexterity and takes only a minute. The shell and the polystyrene foam liner have to be joined. They're adjusted one inside the other, then solidly secured with adhesive tape. The helmet is now completed. And now it's ready for packaging. The safety helmets have to be certified, guaranteeing their safety, and conformity tests are done. At least one helmet in 500 will undergo this destructive test. Here it drops vertically onto a piece of steel. This facility can produce up to 4,000 helmets daily in hundreds of models and over 500 variations. Look around and you will find it. Used for everything from jet planes to cans, aluminum, light and strong, has earned its reputation as the wonder metal of the century. Aluminum, so widely used today, and the world's most abundant metallic element, does not occur in a natural state. The most available source of aluminum is actually bauxite. Bauxite is mainly mined in tropical countries and carried by boat to the Quebec port of La Bay. The aluminum atom in bauxite is bonded to oxygen molecules. These bonds have to be broken by electrolysis to produce pure aluminum. Bauxite is carried by rail to the plant where it will be crushed. Then, through a chemical transformation called the Bayer process, alumina is extracted. This is then roasted in calciners to eliminate all moisture. This is alumina. It is transported by rail to the reduction facility. This plant has 432 pots in which a powerful electric current will be passed to produce electrolysis. An overhead crane dumps alumina into the pots. Then the electric current from the anode placed in the alumina passes through the alumina, which we see here right at the bottom of the pot. Via the process of reduction of the alumina at 950 degrees centigrade, the anodes lose volume and will have to be replaced. It's a continuous operation. Each anode has a lifespan of about 20 days. Spent anodes are recovered from the pot with this overhead crane and carried off to be recycled. They clean the aluminum rods, which will then be reused. Here we see the crust formed atop the anode. When the anodes are replaced, the accumulated impurities have to be recovered from the top of the pots. This is accomplished with these pincers. Then a new anode is inserted into the alumina and electrolysis continues. The electric current breaks the molecular bonds. The heavier aluminum collects at the bottom of the pot, while the oxygen bound to fluorine is released as a gas which is drawn off and treated. The liquefied aluminum remains at the bottom of the pot. It has to be recovered in this huge crucible with a tube. The tube is dipped into the bottom of the pot and a vacuum system draws the molten aluminum from the crucible. The aluminum is recovered in a short time. Air is vacuumed from the crucible by a flexible pipe held by an operator. The tube is finally withdrawn and the overhead crane dumps another quantity of alumina into the pot. Thus, the aluminum fabrication process continues uninterrupted. The crucibles filled with molten aluminum are transported to the casting house. Their contents are poured into holding furnaces which have a capacity of 60 tons. In these very hot furnaces, the molten aluminum is stored to await casting. Finally, casting begins. The aluminum is either semi-continuously vertically cast, producing ingots, sheets, or billets, or directly cast into semi-finished products. The cooling of aluminum pieces is accelerated by water sprays. The large rectangular ingots, which can weigh up to 25 tons, will head for hot rolling, eventually leading to fabrication of products such as aluminum foil. From 4 to 5 tons of bauxite have produced 2 tons of aluminum, which in turn produces 1 ton of aluminum. This particular plant produces 200,000 tons of aluminum annually, yet some other facilities can turn out as much as 400,000 tons. When driving, avoiding skidding during a panic stop was nearly impossible. Today, new brake technology, which is computerized and highly sophisticated, is actually making it possible. Brakes are absolutely essential equipment for every vehicle to slow it down and stop. And brakes have remained practically unchanged for the past 40 years. Conventional disc brakes have pads which press against the brake disc attached to the wheel. These pads grip the disc on only 15 to 30 degrees of its circumference. This develops high heat, wheel skidding, and results in premature wear. The new floating disc brakes have 2 pads of friction material on 360 degrees of the disc circumference. When the brake is applied, hydraulic pressure activates the diaphragm, which applies pressure on the inboard pad, which is then pressed against the disc. In this animation, the diaphragm movement is exaggerated. However simple, the design of this brake calls for some complex development steps. It all starts on the monitor screen with computer-aided design. This powerful software creates objects in 3 dimensions which can be virtually manipulated. They then proceed to digital analysis. Here, digital models are submitted to repeated braking to verify that the parts conform to design objectives. The software verifies changes in heat, the effects of vibration, and resistance to breakage. The right choice of materials is critical. The electrical components also have to be created. Here we see the delicate construction of tiny sensors which measure the force exerted by the braking system. The sensor is the main component of the intelligent ABS braking system, which functions more efficiently than traditional anti-skid systems and reduces braking distance. Then it's the fabrication stage of prototype parts which will be tested. The machining of these parts must take into account the requirements of mass production. This high-precision, robotized machining is done by computer-controlled digital machines. A liquid sprinkled on the machine part cools it during the process. The finished parts are precisely measured, then fitted and assembled to form the total braking system, which will be first tested in the laboratory. Brakes in full contact have a friction surface 6 times superior to traditional brakes. The use of aluminum and composite materials allow for a weight saving of 2.5 kilos per wheel. This affects road holding and reduces fuel consumption by 0.1 liter per 100 kilometers. They proceed to power and endurance tests on this dynamometer, in which a brake and wheel assembly act against a large rotating drum. These lab tests are critical since they can detect any defect in a braking system before it's installed on an actual vehicle. To evaluate the power and endurance of the brakes in full application under extreme conditions, they were installed on this Porsche 911 Turbo entered in the Motorola Cup. They proved completely satisfactory, and the Porsche went on to record many wins. Once all validation tests are done, we move on to the next step. Brakes are installed on a production model vehicle. With data systems, engineers can observe the performance of brakes under all conditions, thousands of times a second. Finally, engineers proceed with actual braking trials with test vehicles. All that remains is to produce brakes on a large scale to supply auto manufacturers' production lines. And that's the story of brakes, from original idea to final product.
The sound of a car starting is like music to the ears when it's -15 outside. Today's batteries are increasingly powerful and efficient, even at the most extreme temperatures. Kind of heartwarming, isn't it? While dissecting a frog in 1786, the Italian researcher, Galvani, noted that when his scalpel touched a leg muscle, it contracted from an electric current produced. Later, Volta believed the current was produced by the metal instruments, the animal being only a conductor. To prove it, he stacked discs of zinc and copper, connected by conductors, and fabric impregnated with an acid solution. And so, in 1800, the electric battery was born. Batteries power all kinds of electric motors. A new lithium metal polymer battery pack such as this one could soon power an electric automobile as well as a hybrid vehicle. This battery will be made up of 4 components. It all starts with this lithium ingot, which weighs about 5 kilos. It's transformed into a thin sheet by this extrusion press that applies 400 tons of pressure. From it will exit a sheet that's only about 250 microns thick. The whole extrusion sequence is closely computer controlled. Extrusion is now completed. The metallic lithium sheet is the required 250 microns in thickness, or 1/4 of a millimeter. The sheet has to be further thinned. Placed on a roller, it is carried to the laminator. At room temperature, it's thinned once again. In just 20 minutes, the 5-kilo ingot will have been transformed into a thin, 250 micron sheet, some 200 meters in length. This laminator completes the thinning of the sheet to between 20 and 40 microns. The resulting 2-kilometer-long sheet will allow for the fabrication of 210 battery units. Lithium is a soft, sticky metal. For this reason, a polypropylene film has to be fixed on the lithium sheet. Without this protection, the sheet would adhere to itself and become unusable. The sheet will be used to make individual battery cells. Then these cells will be assembled in series and in parallel and inserted into modules of different shapes. To make an individual battery cell, the sheet has to be rolled up. This automated spooling machine winds up the lithium film in 26 revolutions. The wound-up sheet is put into a vacuum oven where the various layers adhere firmly to one another. This step lasts for about 90 minutes at 80 degrees centigrade. Here, a test is made. Using a voltmeter, the battery is checked to see that it produces the required 3.56 volts. Any problem can be detected here and corrected. A final quality check is made with this caliper, which precisely measures the thickness of the battery cell. The battery cells are then stored. Metallic plates are placed between them for the entire storage period. One more step remains, and that's the metallizing of the contacts. The battery cells are sent off to a fabrication facility in this container. The container is robotically handled. First, it's put into a protective tank. Then the metallizing of the contacts is done by spraying on molten metal. This takes just a few seconds, since the metal cools very quickly. The battery is now finished. It comprises 4 elements: lithium, which acts as the anode, a metallic oxide cathode, a dry solid polymer electrolyte, and a metallic current collector. All that remains to be done is the assembling of the individual battery cells into a module. It begins with the placing of individual cells onto one another and isolating them with foam so that they don't touch each other. These red sheets are actually heating elements since the lithium metal polymer cells function at temperatures of between 40 and 80 degrees centigrade. All of the individual battery cells of the completed module are connected to an electronic card located above the module. The finished modules are connected to one another in series and in parallel to form a battery pack, which can be used in an electric automobile or a hybrid vehicle. Here we see these modules of a battery pack for a hybrid vehicle, an automobile that works with a gasoline-powered motor and an electric motor. This prototype battery was created for a totally electric vehicle. It surpasses heavy traditional lead-acid batteries that can't develop the same amount of electrical energy and which have much shorter lifespans.
I hope you enjoyed our show today. We wanted to take you behind the scenes to the world of manufacturing. I'm Mark Tewksbury. See you next time on How It's Made. Hello everyone, I'm Mark Tewksbury, your host for this program. Our goal is to reveal the methods and materials that turn out the products we see around us every day. If you think you know something about these items, you might be in for a surprise. There's a whole world waiting for us to discover here on How It's Made. Why worry about light bulbs burning out when you've got spares? Well, today researchers are working on an eternal bulb made of gallium nitrate. It actually burns 5 times less energy than the incandescent bulb we've known since Thomas Edison's 1879 invention. I guess we're ripe for a change. On today's show, aluminum screw caps, chocolate, pills, and pasta. Okay, so it's not as sophisticated as uncorking a fine bottle of wine, but aluminum screw caps are airtight seals for bottles and jars, and they're recyclable.
There are hundreds of everyday objects that are capped. This plant makes 250 million metal screw caps yearly in 12 different sizes. The caps are made from these 1 square meter sheets of aluminum weighing 450 grams. Some 3,500 thin aluminum sheets pass through this feeder. They begin by coloring the aluminum sheet with a colored varnish, a lacquer, and an ink. Then 12 minutes of drying is needed. The sheets that have been colored set off on a conveyor for drying. Then designs are produced. The coloring is applied by this varnisher. The aluminum sheets pass through the varnisher one at a time. Here we see the sheet printed. Above are the colors used. They are highly colored inks that adhere well to metal. Suction cups grab the sheets and send them toward the transport system of the punch press. This press will give the caps the required shape. But the caps have to be machined in successive steps by molds such as this one. The punches first cut the caps. Over 500 caps a minute can be produced. The blades of the punches are made of carbide, a very hard metal that can cut tens of millions of caps. At the exit point of the punch press, the caps are formed but don't yet have the right dimension. This stretching press performs the last 2 cold-forming steps so that the tube will have the required length. Now for the second stretching. This achieves the desired diameter. When the cap exits the press, it will finally have the desired dimension. At this point, the cap now has the required shape. The caps now have to be decorated to the client's requirements. The lateral imprint is made with this silk screen type decorator, which colors some 100 caps in 60 seconds. The decorator uses an ink specially formulated to adhere to metal. The caps will then dry in a warm air oven. The dried caps are ejected and fall into a container. This other flexographic type of decorator prints 155 caps a minute. Here we can clearly see the ink roller which imprints the side of the caps as they rotate against it in a steady stream. All that's required now is to form the cap and make the cut. The profiling and jointing machine makes the cuts and reliefs on 200 caps per minute. Machining the cap takes but a fraction of a second. They sometimes have to assure the water tightness of a container such as a wine bottle. For this, a polypropylene liner is inserted which hermetically seals the container. A check is carried out under a light to verify whether the cut has been properly made and the ridges well formed. At last, the final steps. This screw tightening machine hermetically seals the caps onto bottles. The 250 million screw caps made here each year call for the machining of 1,000 metric tons of aluminum.
If you're young at heart, you might dream of working in a candy or chocolate factory. Oh, how sweet it would be. Well, at least for a little while.
These delicious chocolate confections are made from melted chocolate flowing into molds. The master molds are first made of wood or plaster of Paris. They are then reproduced as copies in an epoxy material. To allow them to become flexible and give them the desired shape, the sheets of epoxy are first heated to 177 degrees centigrade. The epoxy sheet is then placed onto the original molds. The sheet is heated, then lifted off. Suction from a vacuum system makes it adhere perfectly to the shapes of the molds. Here we see the epoxy adhering to the master molds. Still hot and malleable, the plastic has to be cooled. A jet of compressed air effectively lowers its temperature. The mold undergoes a visual inspection to make certain of its quality. And now we move on to the chocolate. This melting unit, whose shell is fed by boiling water, is like a double boiler and melts 1,500 kilos of chocolate in 12 hours at 40 degrees centigrade. The ready-to-be-filled plastic molds are placed onto a conveyor. Filling is done automatically. Liquid chocolate runs directly into the molds. This particular machine produces 400 hearts a minute. The hearts are filled with a concoction of chocolate, cream, and coffee, which has been brewed for several minutes. It takes 20 minutes for the chocolate to set as the molds move along on this 9-level conveyor. Well hardened, the hearts arrive at the unmolding point. The molds are turned over and a rod lightly taps them on the bottom to allow the chocolates to fall out without being broken. Here the chocolates fall out onto a sheet. As soon as they've been emptied, the molds return to the starting point on the line to be newly filled. During their transport on the line, the chocolates complete their cooling and hardening. Now they're going to be prepared for packaging. Packaging depends on customers' preferences. The chocolates can be sold in bulk or placed into boxes. Here, 185 hearts are put into each box. Like the pure chocolate, white chocolate comes in as slabs before melting. Milk chocolate is often delivered in the form of 3-centimeter pastilles. Some chocolates are hollow. They have to be molded in 2 halves. These chocolate bears need special decoration applied by hand before the pouring of liquid chocolate. This decoration is made of white chocolate to which a colorant is added. In just 1 hour, they will make 1,200 bears. They're made by joining 2 hollow chocolate halves. The assembly is done using a refrigerated rotating machine. This machine turns the molds a full 360 degrees on 2 axes and vibrates the chocolates to prevent the formation of air bubbles. The chocolates rotate for 5 minutes before being sent to the cooling conveyor, where they will remain for another 20-minute period. And now they're ready. At this point, the bears are unmolded and they head off for packaging. Each year, this company processes 500 tons of pure chocolate. Many thousands of products are made here using 400 different molds in a variety of sizes.
Take 2 of these and call me in the morning. Who hasn't heard that before? But how many of us, including physicians, really know how drug companies make pills?
Medications are essential in the treatment of illnesses. It begins by a grinding process where the active ingredient in a tablet or pill is ground and mixed with a binding agent. The quantity of the ingredient needed to be ground is transported to the dryer in this container. Like all the other equipment, this container is made of stainless steel so as not to contaminate the product. The temperature of the dryer and the airflow are programmed with this interface. The granulation has to be dried at 40 or 50 degrees centigrade before being shaped into the desired tablet form. Molding of the pills is done by this press, which crushes the powder. The press exerts a pressure varying between 2 and 5 tons. Here's how the molding is done. The press magazine distributes the powder in molds made of steel discs. 2 stampers, one above and the other below, crush the powder and form the pill. Here the press operates at full capacity. It can produce 5,000 pills per minute. Quality testing is carried out on 5 pills every 15 minutes. Their hardness is verified with this apparatus, in which jaws crush it with a force varying between 2 and 20 kilopascals. The pills must now be coated so that they won't crumble. A coating solution made of water and coloring pigments is used. This is the coating unit. It can hold 160 kilos of pills. 3 plastic tubes, positioned at strategic points, will spray the solution onto the pills in motion. The quantity of dry pills to be coated is put into the unit. Then the door of the coating unit is carefully closed. A drum turns inside the unit, tumbling the pills. Then nozzles spray the solution in the form of a mist, which quickly dries, preventing the pills from sticking to one another. This spraying operation lasts 40 minutes. Here we can compare pills. On the left are those made only of powder, while on the right are the spray-coated ones. The finished pills move down a chute to enter a counter prior to filling bottles. They are lined up in grooves to make filling easier. The quantity of pills to be placed into bottles is controlled by this automated unit connected to the counter. In this instance, 500 pills are poured into each bottle. This plant also makes capsules where the ingredient is not crushed but encapsulated in a gelatin casing. The distributor places the two halves of the capsules in the proper position for filling, with the wider half situated above. The top and bottom portions of the capsule are separated. The lower half is then filled with powder. When well filled, the two halves of the capsule are joined together. The completed capsules are then ejected from the filling unit. Then, via centrifugal force, they are positioned for the packaging process. The weight of each capsule is verified by this counter. Each capsule must have the precise weight. And the final step is packaging. A sheet of transparent PVC is heat embossed, forming an impression to receive capsules. Then a pre-glued aluminum foil sheet is adhered to the backside, sealing everything in. This plant turns out millions of pills and capsules every year.
This is what Italian traveler Marco Polo brought back from China some 700 years ago. Since then, pasta has spread all shapes and sizes, and so have we pasta lovers. But that's another story. Who would have thought that pasta is actually Chinese in origin? When Marco Polo returned to Venice in 1295, after spending 24 years in the Far East, he brought back with him Chinese pasta noodles. So quickly popular did pasta become that by the 15th century, it occupied a prime position in Italian cooking. In this same era, commercial production began in Naples. Italians today favor macaronis and raviolis with garlic and cheese. Pastas are generally made from semolina and water. These silos contain more than 30,000 kilos of semolina derived from durum wheat, a hard, amber-colored wheat. The semolina heads toward the high-speed premixer, where it will be vigorously mixed with water for 5 to 10 seconds. This machine can treat between 1 and 2 tons of semolina per hour. The dough is extracted from the premixer and falls into a first blade mixer, open to the air. Then the dough goes into this vacuum blade mixer. The mix is now ready to go through the brass molds. Here's a spaghetti mold and a mold for mafalda, very narrow lasagna. And here are molds used to make lined shells and stars for soups, as well as cresta di gallo. The dough is injected into the mold under pressure. This rotating blade machine cuts some 12,000 rotinis per minute. That's 720,000 per hour. With the dough being still quite fresh, the rotinis are soft. They will dry somewhat on this plate. Now we move to the lasagnas. The dough goes through this brass mold, and the strips of fresh dough, 107 centimeters long, are placed on these sticks to dry at 65 degrees centigrade. They dry vertically so as to retain their nice flat shape. After drying for 15 hours, the strips are then cut in 4, thus making 4 strips measuring 25 centimeters each. To minimize losses and make cutting the dry lasagna easier, scissors trim the dough pieces into equal lengths on the sticks. The long lasagna drying process begins.
Once dry, the lengths of lasagnas are finely cut. They're now ready for packaging. To make some other pastas, the mix has to be a bit more worked in order for it to have the required shape. The dough goes through this roller, which gives it the desired thickness. And now butterflies are formed. This mold cuts 7,500 of them a minute, for a total of 450,000 an hour. The sheet of dough is 61 centimeters wide. It is produced in a steady stream and goes right to the cutting mold. The butterflies fall onto this conveyor to dry somewhat. Then they head toward the next production step. Certain short pastas, such as these butterflies and fuzzilis, have to be dried, so then they're put into this full dryer. Coming out of the dryer, the pastas are hard and ready for packaging. Here we see the ever-popular spaghettis being made. As with lasagnas, spaghettis are also dried vertically. Now this automated machine places the spaghettis onto a cutting table and breaks them to the proper length. The spaghettis are now ready for packaging. Exact quantities to be bagged are determined by computer. Then the spaghettis go gently down this chute. The amount of spaghetti going into each bag is transported and emptied out by this moving container. To make filling easier, the spaghettis are properly positioned by this chute. In just 1 minute, this machine can package 10 4-kilo bags. Whenever needed, it can handle up to 60 bags a minute. Pastas are a favorite meal the world over. This plant makes over 100 different products, and every day uses between 60 and 360 tons, or the contents of from 2 to 12 truckloads of semolina made from hard wheat.
I hope you enjoyed our show today. We wanted to show you the behind the scenes of the world of manufacturing. I'm Mark Tewksbury. See you next time on How It's Made.